Hello, my name is Michalis Famelis, and I'm going to be presenting to you the paper Checking Temporal Patterns of API Usage Without Code Execution. This is work that was done by Eric Riley-Jean, myself, and Hori Sahrawi at the Geode Software Engineering Research Lab at the University of Montreal. I'm going to start with saying that IDs are awesome. They allow a programmer, like Adele for example, to write code and write code in the IDE, and then the IDE immediately would give the programmer a whole bunch of very useful feedback, things like code auto-completion or maybe code generation, organizing imports, compiling things on the fly and providing immediate feedback. So this kind of feedback loop between a programmer and an IDE is an excellent boost to productivity, which is why IDEs are like a necessary staple of contemporary software development. We're focusing on a particular use case of IDEs though, and this is a case where we think that IDEs are not as awesome as they could be. So imagine that a software engineer, our software engineer here, is trying to use an API, an Android API. What she would have to do is she would have to amass a whole bunch of knowledge, read and understand documentation, look for examples, seek community support, things like that. And based on all of this information that she would have to amass in her own head, she would then write code and then send it to the IDE, and the IDE would give feedback. But that feedback would not be tailored specifically to the API that she would be using. To get information about that, like am I using the API correctly, for example, she would have to depend on feedback from other sources. She would have to look at the execution traces, at bug reports, community support, etc. So the fact here is that this loop, this beautiful feedback loop that we had that I showed you before, has now been broken up into two different parts. The part where the IDE gives you this generic feedback and then you have to supplement that with extra sources of information. And this does not give you the kind of productivity that we would hope to have. So what we envision is the following case, where what if we could take all this knowledge that Adele would have to amass and crystallize it and put it inside of the IDE. So now you have an IDE that is capable of leveraging knowledge about a given API. So now this, we claim, would improve productivity and would also give we would be able to make sense of whether we're using an API correctly. So it would allow us to have more confidence that that we're using APIs in a safe way. So this is our vision here. Our vision is again to integrate knowledge about APIs inside of the integrated development environment. So here's how we thought to go about this. We built an approach called the Temporal Usage PAttern Checker, Tupac, for APIs. And what Tupac does is the following. We thought to leverage the big body of work that exists, where a lot of people have spent a lot of energy trying to build methods and techniques for extracting knowledge about APIs from all sorts of sources. So there exist many API property pattern inference techniques. And what we want to do is we want to take these temporal patterns and integrate them inside of the IDE in a way that makes them useful to the developer. So this is what our contribution really is, and what the challenge here is how can we best integrate knowledge about this knowledge encapsulated by this temporal API usage patterns in the IDE. The main challenge here is that we want to be able to do this with using static analysis, and also we want to be able to do it for programs that are not guaranteed to be complete and executable. Because when you're writing code in your IDE, your code is not guaranteed to be able to, for example, run and to run or to run enough to be able to execute a particular test case, right? So this is what the main contribution and challenge for Tupac is. So let me dive in a little bit to tell you more about how Tupac does things. First, let me lay down some basic assumptions here that we're making. The first one is that we are assuming an object-oriented paradigm. And the second is that we want to integrate our tool in the IDE. We want the IDE to be able to leverage these property patterns as part of the regular coding rhythm of developers. We don't want the developer to have to stop, go consult some external source, then return. We want it to be usable within the regular cycle of write, save, compile, and so on. So we want the feedback to be easily integrated into this kind of coding rhythm. This means necessarily that we need to be able to work with incomplete code, right? So this is one of the big challenges here, and for this we necessarily need to be talking about static analysis here. We need to be able to do this without having to run code, without relying on test cases and traces and things like that. So we want to be able to do static analysis of incomplete code. We're assuming again this usage patterns as external inputs. So we do not provide a particular method for extracting temporal API patterns. We're assuming that one of the many techniques that are specific for this have been used, and now we have a bunch of temporal API usage patterns. This can have been done, for example, from documentation or from a tool that extracts them from traces or whatever. And we're assuming also that these properties are encoded in a temporal logic. In our particular case here, we're using linear temporal logic. So, given these assumptions, here's what Tupac really does, right? So at the beginning, you give Tupac your code. So Tupac assumes that there's some code in an IDE, and from this we're extracting control flow graphs and call graphs. These are some artifacts that can be extracted using static analysis from the code. Then there's a step where these artifacts are combined to produce what we call the deep graph, and then this deep graph is encoded into the language GnuSMV, which is a language used by an off-the-shelf model checker. In our case, we use GnuXMV, as well as the temporal API usage properties encoding in linear temporal logic. So using these two inputs, we pass these inputs to a model checker to get feedback. And Tupac integrates this into the IDE and provides feedback back to the user. The core concepts of this approach are the following. So I mentioned some of these words already. Let me explain what they mean in case. So we have one concept is the control flow graph of a given method. The control flow graph is a graph that its nodes are instructions and its edges represent the passage of control. If you have instructions such as an if statement, for example, you would have a node with two outgoing transitions, with two outgoing edges. You could use the control flow graph if you wanted to only analyze the code of a single method. This is called intraprocedural analysis. So if we wanted to just do intraprocedural analysis, we could just be using these control flow graphs. If we want to do interprocedural analysis, so that means analysis across methods, then we need something like the call graph, which shows callee relations between methods of our system. And this captures interprocedural dependencies. That is a type over there, interprocedural dependencies. So the control flow graph shows the intraprocedural passage of control. The call graph shows the interprocedural dependency, callee relationships. The deep graph of a system integrates these two, combines them into one representation, where we show both the instructions and the passage of control, as well as callee relationships. And here its control transition is annotated with the method that triggered it, with the method that called it. On this deep graph now we can define the notion of a trace, which is a path on this deep graph. Such a trace is a potential execution trace. If we were able to execute the code, it could be one kind of way of, it could be one execution trace that this code could produce if executed. But the deep graph also contains more behaviors than what the code might actually end up producing. So it is important to understand that that the deep graph is in this sense, it is a lossy abstraction. It adds more behavior to the code. However, the trade-off again here is that we are able to do this analysis even though the code might be incomplete. Okay, so we are operating in an environment where we have incomplete code, so therefore we think it is potentially acceptable to have these extra behaviors to analyze. So these are the core concepts, and based on this, in the paper you can find an algorithm for constructing this deep graph. The idea is you get as inputs the set of control flow graphs of the system, and it's called graph. The first step is where we prune and slice these inputs to only keep relevant things like just the API calls and just the calls of the system itself, of our own methods, as opposed to, for example, library methods or calls to APIs that we are not interested in analyzing. That's the first step. The second step is we annotate the edges of the control flow graphs based on information from the call graph to understand what method has triggered each passage of control, and then this gives us a set of annotated control flow graphs, and then we connect all of them. We connect this forest to get this deep graph. Just to make this a little bit more concrete, let's take this little example here. We have a method. We have a class data manager has two methods. One is called save close, and another is called save release. And save close calls the method save release, and so you have one method calling another, and then these two methods also contain calls to the SQLite API, the Android SQLite API. So I imagine we're trying to understand, we're trying to analyze this kind of code. So the first step is we start from the call graph of this code. We start from the entry point method, where we get its control flow graph, and then we follow the different caller-callee relationships to expand and find the control flow graphs of the other methods of the system that we're analyzing. And the idea is that then we want to put these expanded control flow graphs inside of this initial control flow graph to grow based on the caller-callee relationships. So given this control flow graph of the save close method, we want to input also the control flow graph of this save release method at this point here. And this is what the construction algorithm does. And it produces at the end, we have this result, this deep graph, where you can see that in this region here is the safe release, the control flow graph of the safe release method that has been integrated in the control flow graph of the method that called it. And following this procedure, that's how you build this deep graph that integrates all of this. And you can, and when you see here, we're annotating, for example, all the control transitions inside of this region using an annotation that means that this has been invoked by another method. So this is what a deep graph looks like. Again, you can find more information about how this exactly is constructed in the paper. And once you have done this, then we can analyze this. We can use a model checker, an off-the-shelf model checker, to check the properties of this, to check the temporal pattern properties on the deep graph. So to do this, we translate the deep graph into the NewSMV language. It becomes a module, and the state of this NewSMV model will be defined by the method and API calls. And the transition relation is defined based on the color annotations, as well as certain additional constraints to enforce determinism. We also take as input API property patterns in LTL. Like we said earlier, these are assumed to have been provided externally for a given API of interest. And once we've prepared this NewSMV encoding and passed it to the model checker, there's two possible results. You either get true, in which case you have the case that the API usage property pattern is respected, so your code is safe with respect to that pattern. Your code respects that pattern. Or you have the result false and a counterexample, which indicates, which means that this pattern is violated. Now, this could either be a true positive, where indeed we have identified a misuse of the API, or it could be a false positive, where Tupac produces a result, reports a violation where none exists. And this kinds of false positives, there could be two sources of these false positives. One is because, like I said earlier, the deep graph is an imprecise representation, so it has more behaviors than the code. But it can also be because the pattern that we're checking is not relevant to the particular code fragment. So that also produces a false positive. In any case, if the result of the model checking is false, Tupac produces a visualization to help the developer make sense of what has happened. So in our paper, we're also presenting a preliminary evaluation of our of Tupac, where we focus on three questions. The first one is how good is Tupac for detecting violations. The second one is comparing interprocedural with intraprocedural analysis. Is it worth to analyze the deep graph? Can you just analyze the control flow graphs, for example? And the third question is Tupac fast enough so that we would be able to integrate it into the regular coding rhythm? So can it be used without stalling the workflow of developers? So to do this, we took 4 open source programs, 4 commonly used APIs from the Java standard library. We produced some sequence calls based on all of these. We took some typical use cases, we collected traces and gathered sequence of API calls, and then we used an existing API mining technique, API pattern mining technique, to get some patterns to check. Again, for our evaluation, we used a technique. Any technique could be used. Tupac is independent of any particular technique. For the first 2 research questions, we used only those patterns that were respected by all the different projects. But then for the third one, where we're interested in scalability and speed, we sampled patterns such that they would represent different degrees of complexity, so patterns of various complexities based on their abstract syntax tree. Okay, so based on this setup, here's what we found. Okay, so the first thing is, the first question was concerned the precision, how good is Tupac for finding problems. Okay, so we first did the manual analysis, and then we compared the results of Tupac, the automated results, with our manual analysis. What we found is that, first of all, Tupac behaves consistently across the 4 different projects that we saw. Usually we have very good recall, and the precision that we get is generally better than random. So you get a precision that is more than 50%. So based on this, we can say that Tupac is reasonably good at detecting violations. The second question that we had was whether interprocedural analysis is worth it, or if it is enough to do just intraprocedural analysis, just to analyze within a given method. Would it be possible to produce some results very fast, right? So could intraprocedural analysis be a cost-effective shortcut to compare to the potentially expensive construction of the deep graph? So we compared again the results of the two, where we had one case where we did the interprocedural analysis, and then we ran the same experiments but using only intraprocedural analysis, using all the control flow graphs. And what we found is that, first of all, you get similar recall, but on the other hand, precision suffers a lot. So the precision of intraprocedural analysis is worse than random. So based on this, we conclude that interprocedural analysis is better than intraprocedural analysis. It is worth it to spend the time to produce this deep graph in order to do this analysis. For the third research question, we were interested in understanding whether Tupac is fast enough to be integrated into the regular coding rhythm. So here we're interested in time. So we found the average creation time for deep graphs, and we also measured separately the average time for that we spend in the model checker, and we looked at the time spent to check all the patterns of a given API, as well as the average time to check one single pattern. One thing to note here is that the times that have to do with the verification of patterns are in a sense independent from Tupac itself. Improvements in model checking technologies would definitely impact those numbers, right? So the essential complexity of Tupac is on the creation of the deep graph. So what we found here is that on average it takes less than a second to create a deep graph, which is acceptable, especially if we take into account the fact that these deep graphs are reusable across different you can check different patterns on the same deep graph, so you don't have to recreate all the time. You need to create a deep graph every time you change your code. In the future, we are also interested in incremental reconstructions of the deep graph, for example. So that's one thing. And then the second thing is that on average, for a single pattern, again, it takes less than 1 second. It can take more time if you're checking a whole bunch of patterns for a given API. So here the result is we say that yes, Tupac can be used without breaking the code rhythm, but it depends how you use it. If you deploy it only for a given pattern, for a single pattern, this can happen within a second and a half, basically. But if you are interested in all patterns, this can take longer. So yes, it can be used, but it depends on how you end up using it. And of course, more optimizations could end up, and optimized deep graph construction and improvements in model checking technology could really help improve these times. Okay, so to conclude, again, our approach, our contribution here is to take the result of many existing techniques that extract information, extract patterns of API usage, and we want to integrate these patterns, this knowledge in the patterns, into an API. And that's our contribution. The key challenge is that we want to be able to use these things using static analysis on potentially incomplete code. To do this, what Tupac does, it takes things like the control flow graphs and the call graphs of a system and produces a thing called the deep graph that integrates these things and allows for interprocedural analysis. And then we use an off-the-shelf model checker to check the properties of interest. We did a preliminary evaluation where we found that Tupac is reasonably good at detecting pattern violation. Interprocedural analysis is actually worth it compared to intraprocedural analysis, and depending on how you set up Tupac, Tupac can be fast enough to use in the regular coding rhythm. Of course, there's many limitations here. There are certain code structures that the existing version of Tupac cannot handle, so things like chained instructions and things like that. And of course, another big limitation is that that Tupac produces false positives and can produce many of them. So ways to improve Tupac would be to include things like vacuity testing to determine whether particular patterns are relevant, and as well to improve the construction of the deep graph to encode to tighten a bit the set of behaviors encoded by the deep graph. Another area of improvement is to help the deep graph distinguish between the different objects that are making the calls, which is currently a source of adding more behaviors to our approach. And of course, we would like to do a more thorough evaluation, validation with users, and a deeper comparison with similar approaches, but there the challenge is establishing a common static analysis benchmark. So, based on this, thank you very much for your attention. This has been, I'm Michalis Famelis, presenting you the work by Eric Religion, Juarez Sahrawi, and myself. where I've talked to you about Tupac. Thank you very much.
Hey, everybody, welcome back. We're now at the last Q&A, and I'm here with Michalis Vermelis. He's with the University of Montreal in Canada. Welcome, Michalis. Thanks for being here. I see there have been a number of questions in the chat already. Some have been answered, partly at least. Simon asked a question about the deep graph rather than the flat graph, and of course there's connotation with deep learning, I see, so that was nice too. The second question by Simon has been answered too, I think. Why does the deep graph have more behaviors? And that's answered by Awari, and in addition by you. So if you want the answer to that, you can read it back in the chat. Then I see a question by Laura Samini. About precision, 47% of true positives, but were positives, also provide pointwise information is better than random. That would say yes, no on the whole program, or am I wrong?
Yes, I wrote in the chat. I'm not
sure. Oh, okay, yes, I see. The question is perhaps not entirely clear, but more than a question is an observation. Okay. Do you want to add to that, Michalis?
Yes, let me read the. If you tool says this, precision. So let me see, the 47% of true positives. That was for the. I think I'm looking now at my slides, and that 47%.
So I can make the question live. Thanks, Simo, for calling me. I mean, you were saying that in some cases you have a very low precision, but which is saying worse than random, but it's worse than random if the tool just tells you yes or no. Okay, say the word program is incorrect, but if the tool also provides pointwise information on where the fault might be, then it's better than random because, okay, it's, of course, it gives you some, okay, this is, yeah, exactly.
I see what you're saying. Yeah, that makes sense. That makes sense. So in that case, you're right about this. That yes, we also, because since we also give the counter example, that might still be useful. I think what the proper thing to do here would be to do some sort of user study or something like this to see whether these counter examples would actually be useful to people. Because yes, like even when you get 47% accuracy, does this the counter example that you're given actually help you improve your program? That would be the real question, I think. But at the same time, I'm assuming we're talking about the second research question, which is comparing intra-procedural with interprocedural. There, what we see is that interprocedural is generally much better. So if we're willing to pay the extra cost, then we get better precision anyway. Again, going back to trade-offs, right? Like the question becomes, because intra-procedural is much cheaper, how much more feedback you can give compared to better feedback versus more feedback. It becomes a trade-off like that, I think.
Yes.
Okay, let's go to the question by Marie-Christine Jacobs, because not everybody seems to find their way to the discussion room. You mentioned incremental construction of the deep graph. Do you have other ideas on incremental analysis? For instance, stop if the deep graph doesn't change, only analyze newly added paths?
Those are all great ideas. We didn't experiment with those. In a next iteration, all of these things we should absolutely look into, right? Yeah, absolutely. Again, the whole point here is to be able to integrate this within the regular rhythm of coding. So whatever allows this to go smoother is absolutely useful improvement here.
Okay, thank you. Hope this answers your question, Marie-Christine. We now go continue in the discussion room. So if you want to join, please.